Hi, Assalamualaikum warahmatullahi wabarakatuh. In this video, I would like to talk about the idea of orthonormal basis, and we call a set of vectors in a vector space here. It is an orthonormal set if it is orthogonal. So the set here has to be an orthogonal set of unit vectors. So what is the meaning of unit vectors? It means that when you calculate the magnitude of that vector, the result is equal to 1. So in order to be an orthonormal set, the set of vectors here has to be not just orthogonal, but also is unit vectors. Okay. And then here is another definition related to orthonormal basis. So orthonormal basis must be a basis of subspace W, so that is one condition, and it also must be orthonormal. Okay, so how can I visualize these two ideas here using a diagram? Well, here we have a set of vectors. So A here is the set of vectors. Okay, so what we can do is we can ask whether are they unit vectors? Are they unit vectors? So the meaning of unit vectors is if you find the magnitude of each of this vector, the magnitude here is equal to 1. So that's the meaning. Okay, so let me just do this properly. So are they unit vectors? So there can be two answers to this question: yes and no. Next, if there are unit vectors, then we go on and check, are they orthogonal? So what's the meaning of orthogonal? It means that when you consider the dot product of all possible combination of these vectors, the answer has to be equal to 0. Okay, so that is how to check whether they are orthogonal or not. And again, there can be two answers to this question: yes and no. Well, if the answer is yes, then we say that A here is orthonormal set. Okay, so this A is called orthonormal set because they have unit vectors and they are also orthogonal. So that's the first idea that is given here. Now let's look at the idea of orthonormal basis. So for orthonormal basis, what you can think of is you can think about having a vector space. Here is the vector space. And from this vector space, there is this subspace. You can think of it as a subset. And I'm going to call this subspace W. So here we have subspace W of a vector space. And from this subspace, we can go on and try to find the basis. To find a basis, there are two conditions that you have to fulfill. The first one here is, let's say we call the basis here B. So in order to be a basis, B has to spans. So B spans the vector space, and B is linearly independent. So that's the idea of basis of a subspace. Okay. Now let's say we have managed to find a basis. A basis consists of vectors. So we can have vector 1, vector 2. Okay, we can represent basis as a collection, as a set of vectors. So up to vector k, let's say we call this. So this is a basis here now. And once you have managed to get a basis, so this is the first stage, what you need to do is you need to then consider the unit vectors. So what is unit vectors? So all these things are unit vectors, which means the magnitude of all the vector here is equal to 1. So that's the meaning of unit vectors. You've got to check that. So the answer to this is either, well, no and yes. So this is unit vectors. Next, once you have checked if there are unit vectors or not, you can go on and check the orthogonal. So the answer to that again can be yes and no. Okay, are they orthogonal? So what is the idea of orthogonal? Well, the idea is that all possible pairs for this vector here has to be, well, when you consider the dot product, it has to be equal to 0. So that is the idea of orthogonal. And let's say the answer to that is yes. Okay, I'm just going to use this space. So the answer is yes. Therefore, we can say that the basis we have here is orthonormal basis. Okay, so that is the idea. It is an orthonormal basis. So B here is an orthonormal basis. And in other words, we are saying that it is not just any basis, but it has a specific name. We call it orthonormal because the vectors in this basis, there are unit vectors, and also they are orthogonal. So that's the idea. Okay, so here is some notes related to orthonormal basis. For example, W is a subspace, and let's say we have orthonormal set. So we already know that here is containing vectors that are orthonormal, which means that if you, for example, consider the dot product of each qi, qj, where I it's not equal to j, the result is 0. And there's another idea to that. If it is orthonormal, then if you consider the product of itself, qi dot qi, the answer is equal to 1. Okay. Now, let's say you already know that here is a set of vectors that is already an orthogonal basis. Based on that, in order to find the orthonormal basis, so we want to find orthonormal basis from orthogonal basis. So this is given, and let's say you are asked to find what is orthonormal basis. There is a sort of shortcut way that we can do it. We can just use the result that we have. Okay, so we can just use this, and then you divide each vector here with the magnitude, so the magnitude of itself. So here is the magnitude of v1, the magnitude of v2, and the magnitude of vk. So by doing that, you will get a new, so here is a new set of vectors, and this set here is orthonormal. So that is the way to find orthonormal basis from orthogonal basis. Now, without further ado, let us do some examples, okay, related to this idea. So here, the first example is asking you to show that the set of vectors here, so this is the set of vectors containing q1 and q2. q1 is given by this, q2 is given by this, and we have to show that S here is an orthonormal set. Well, we are going to just follow that simple idea. If it is orthonormal, that means when you consider the dot product of q1 and q2, since we only have two vectors here, the result has to be equal to 0, and we have to show that. Okay, so I'm just going to write down the vectors here. So this is 1 over square root 3, negative 1 over square root 3, 1 over square root 3, and q2 is 1 over square root 6, 2 over square root 6, 1 over square root 6. Well, if you multiply the first component with the first component, you will get 1 over, this is a square root and this is a square root, so you can combine the numbers together. So under the 1 square root, so here is 1 over square root 18. For this one and this one, when you multiply them, you will get negative 2 square root 18. This one and this one is plus 1 square root 18. And this is equal to 1 minus 2 plus 1. Combine everything together. Therefore, the numerator part here is going to be 0. So 0 over square root 18 is just 0. So that is the dot product of distinct vectors. And also, if you want, we can try and demonstrate that the result of this is equal to 1 as well. So we can do it. Maybe we can start off with q1 dot q1. So here we have 1 over square root 3, negative 1 over square root 3, 1 over square root 3. Multiply by itself. Okay. And we're going to consider multiplying by components. So the first component is, well, you have square root 3 and you have square root 3. When you multiply together, square root is going to be like gone, eliminated. So here we have 1 over 3. 1 over 3, negative 1 over square root 3 with this one, you will get negative 1 over 3. So be positive, actually, negative, negative, positive. Positive 1 over square root 3 with itself. And here is just 3 over 3, which is equal to 1. Okay, and I'm not going to show this, but you can do it on your own. Then you can consider showing that the dot product of q2 and q2 must be equal to 1 as well. So that one is do it on your own. Alright, and since we have fulfilled these two criteria here, then we can conclude that, well, therefore, the set vectors here, the set of vectors here, which is called S, we can say that is an orthonormal set. So is an orthonormal set. Okay. Right. Now in this question, it is asking you to construct an orthonormal basis for this vector space here. So we've got these following vectors. Now, if you want to construct the orthonormal basis, what you can do is you should actually follow this procedure given here. So again, what we have is we already have given here. So here is the set of vectors given. So here is already the set of vectors, and I can call this set of vectors as A if I want. So A consists of v1, v2, and v3. So I already have this particular set, but in order to be an orthonormal basis, so in this question here, they give you a set, and we call it A. So before we can do anything else, we need to make sure or to determine, is it a basis? So is it a basis? So in order to determine if it is a basis or not, you have to do all this thing. You have to show this. So once you show this, you have to then establish, you then manage to establish that if you manage to show these conditions are fulfilled, therefore we can say that A is a basis, and we follow this procedure. We have to check, are they unit, are they orthogonal, and so on. Okay, based on that, we can say that A here is orthonormal if it fulfills all this idea. Okay, well, so that is the process. However, in this particular example, we have actually done this example, and we have done this example. Let me just write. We have done this in the previous video, and we have demonstrated that this here A is orthogonal basis. We already demonstrated that. So since we already know that this is an orthogonal basis, we don't need to go through all this process here. We can just use this idea. Because we already know that it is an orthogonal basis, we can just use this idea and find the orthonormal basis using this given formula here. So that's what we are going to do. Therefore, in this example here, the orthonormal basis will just be, okay, we have to use this formula, vector 1 divided with the magnitude of vector 1, vector 2 with the magnitude of vector 2, and vector 3 the magnitude of vector 3. So by doing that, we will get a new set. So here will be new set, and this new set is going to be orthonormal basis because it comes from A. A here is already an orthogonal basis. Okay, therefore, let us start by finding what is the magnitude of this vector. So the magnitude of vector 1 is just the square root of, each value here has to be squared and added. So 2 squared plus 1 squared, okay, plus negative 1 squared, and this is 4, 1, 1, so square root of 6. That is the magnitude of vector 1. And then the magnitude of vector 2. So I'm just going to write down all the magnitudes here. So magnitude of vector 2 is just, well, the square root of 0 squared plus 1 squared plus 1 squared. So this is the square root of 2. And finally, magnitude of vector 3 is the square root of 1 of all these components here. The values here squared and added. 1, negative 1 squared, 1 squared. So here is just square root of 3. Okay. Well, therefore, the orthonormal basis is going to be equal to these values. Let me just erase a bit this space. So therefore, the orthonormal basis is going to be each component here will be divided with a magnitude, so it will be 2 over square root 6, 1 over square root 6, negative 1 over square root 6. So this is the first new vector in the orthonormal basis, in the set of orthonormal basis. Next is, well, for this one, 0 divided with the magnitude is going to be 0, 1 over square root 3, sorry, square root 2, and here is 1 over square root 2. So this is the second vector that we have. And then finally here, 1 over square root 3, negative 1 over square root 3, and 1 over square root 3. Okay, so this is the answer for this example here. Okay, it is very easy. What we need to do is just we use the set of these vectors here. So these are already orthogonal. Okay, orthogonal, and then you use this, divide with the magnitude of each vector, then you will get the new set which is orthonormal. Okay, I think that's all for now. Thank you very much for watching, and I'll see you in the next video.